Hello everyone, welcome to our new lecture. I'm recording this Sunday evening, so hopefully this is actually uploaded in time for class Monday afternoon, which maybe is the first time I'll be doing that for this class. So I'm going to imagine that you're very pleased with me and saying, oh, that's great, Professor Plick, you're the best. Anyway, okay. Today is lecture number 17, still on chapter 11. We're going to go over stuff that's on pages 542 to 568. For next class, nothing to read and no homework, right? You should be turning in your homework around about Monday evening, right? So no new homework, but then of course you do have that exam on Wednesday. I have like a little piece of filament. Yeah. So today we're going to continue to talk about nuclear decay. We're also going to go into more detail about the nuclear force, right? We'll talk about why the nuclear force is so difficult to deal with. And we'll talk about nuclear reactions. And how much we talk about that will just depend on how much time we have. Okay. So, where is this? Still hot. Okay. So there are three processes that we talked about for decay, right? There's alpha, beta, and gamma. We talked about alpha and gamma. Now we're going to talk about beta decay, which is the most complicated one. So there are three processes in total where the atomic number A stays the same, but the neutron and proton numbers, that is N and Z, change. Okay. So this happens as neutrons and protons change into each other, right? Remember that neutrons and protons are each made up of three quarks. These quarks are bound together by the strong nuclear force, the strong nuclear force directly. So in total, three quarks make up neutrons and protons, right? But you can imagine that if we slam neutrons and protons together or do other stuff to them, right, they can change one into the other because the internal dynamics of these quarks can change. Right? So there are three processes. So there's three types of, or broad types of nuclear decay: alpha, beta, gamma, and then beta decay itself is a result of three different processes. We can have beta, we can have beta minus decay, and that is when a neutron turns into a proton plus an electron. We can have beta plus decay, and that is when a proton changes into a neutron and a positron. And there is EC decay. And the proton and an electron together change into a neutron. Okay. So if we were in class, I would invite you to realize that there's something suspicious about these conversions, right? So they conserve charge. Right? A neutron turns into something that's positively charged and something that's negatively charged. A proton turns into something that's neutrally charged and positively charged, positron. And then also the proton plus an electron with a positive and negative charge can turn into a neutron with no charge. Okay. But something else is awry, and what I invite you to do is go back into your notes when I was talking about conservation laws, and I had the list of conservation laws, and I said, oh, all these have to be maintained in any kind of reaction in total. So go back to that list, pause, and now look at these guys and see if you notice anything fishy about them. Okay. So the thing that they do not conserve is spin and lepton number. Okay. So lepton number, if you just looked at your notes, are fermions that do not feel the strong nuclear force, which specifically one example of that is electrons and positrons. So here we have no leptons, here we have a lepton, here we have no leptons, here we have a lepton, here we have a lepton, here we have no leptons. Okay, so lepton number here is not conserved. Also spin is not conserved, right? I have another additional half integer spin here, half integer spin here, half integer spin here, and the spins don't add up on either side of these equations now. Okay, so these processes, which are observed, would seem to violate these two conservation laws. Okay, there are also some other inconsistencies with these types of reactions with conservation of linear momentum and conservation of mass energy. So if you were to just observe these processes taking place, processes of the various beta decays, right, you would think that there's something wrong about them. Well, in 1930, Wolfgang Pauli proposed a solution, which is that a very small mass particle with neutral charge existed to balance out these equations. Okay, so, don't really. All right. So in this line here, we have another particle, which I'll explain in a minute, but nu, this is the Greek letter nu, sub e over bar, and nu e, and nu e. Okay. So in 1933, Enrico Fermi formalized this proposal, the one 3 years earlier by Pauli, and he called this particle a neutrino, which was Italian. Enrico Fermi was Italian, which is Italian for little neutral one. Okay, so this guy here, nu sub e over bar, that is an electron antineutrino. Okay, and then nu e without the over bar is just an electron neutrino. In particle physics, the over bar can be used to indicate an antiparticle. There's not one with the positron because we also have this little plus sign here, right? Whether we have an electron or a positron. So there are three types of neutrinos. There is electron neutrino, there is the tau neutrino, and there is the muon. I hope I wrote this down. Pretty sure it's the muon neutrino. One for each lepton. I'm going to look this up real quick. Pause. Pause. Unpause. Yeah, it's electron neutrino, muon neutrino, and tau neutrino, right? Those are the three leptons. Each lepton also has its own flavor of neutrino, right? And then there's 6 in total because each of them can have an antiparticle. Sorry, Sorry, my cat's meowing. So, what are the characteristics of neutrinos? And you might be suspicious of them because they were just apparently made up to make equations balance, but it turns out it was correct to make them up because they exist. So a neutrino, very small mass, and by very small, I mean by far the smallest. The mass of a neutrino is really, really teeny, 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 tiny. In fact, there was and still is debates about whether all the neutrinos have mass. Because they're so small, it's so difficult to deal with. They are also leptons, as the electron tau and the muon that they take their names from, which means that they don't feel a strong nuclear force. Right? They also don't feel the electromagnetic. Right? It looks like if I move over to the board, it gets very white. What is that? That's so annoying. Okay, if any of you are like good at shooting videos and knows why this is happening, I would appreciate you emailing me and telling me. Maybe because I'm recording this in the evening and the light is a little weird coming through the window. See, now you can't see it. Now you can. Well, I'm going to close my blinds and maybe that'll change the lighting in here. Okay, I closed the blinds and put on some lights in here. I think maybe it's helped a little. Difficult to tell though. Okay. Again, if any of you know how to make it so that that doesn't happen, I would be appreciative. Like if it kept the same luminosity as I was writing. Where was I? Yeah. So leptons don't feel the strong nuclear force, only the weak nuclear force, and gravity. Right? They of course do not feel the E&M force because they are electrically neutral, so they have no charge. Okay, and they are spin 1/2. Right, they're fermions. Okay, so as well with leptons are fermions, so they also have spin, integer spin. In fact, spin 1/2. Okay. So these balance out our beta decay equations. So let's look at an example of a beta plus. So a beta plus example would be nitrogen changing into carbon plus a beta particle and an electron neutrino. So a positive beta particle is a positron. Right? If you remember from the last board, maybe I stayed over here, makes it more legible. When I see it close, it gets brighter. Stand further away. Maybe if I turn off this light also. Nothing's ever easy. Nothing ever. Okay. And then an example of a beta minus would be gold turning into mercury plus beta minus particle plus an electron antineutrino. So that beta particle here, of course, is an electron. So these beta decays are really energetic electrons or positrons. The only thing that makes beta decay different from alpha decay is that the particle radiated did not, well, that's not the only thing. Oh no, my notes are correct. One thing that makes beta decay different from alpha decay is that the particle radiated did not exist before the decay. So we saw with those alpha particles, those ionized, doubly ionized heliums, right, 2 protons, 2 neutrons, that they existed in the nucleus beforehand, and they tunneled out through that potential barrier, right, and then they were able to escape to the continuum. Maybe if I stand here, yeah, here it's, for some reason, if I'm closer, it's clearer, but then, I think maybe I just need to be sure to film these things in the morning. But then how do I do 2 in one day if I have to do them both in the morning? Suppose I could record them in the morning and upload them in the evening. That's what I'll do. And maybe that'll make, okay, maybe you guys go in your email and tell me which of the videos was easiest for you to make out so far. And then, no, that's not helpful because then the weather conditions. Today it's overcast, which is maybe another problem. If any of you know about lighting, tell me what to do. Hopefully this is all legible. I'm trying to make it so that it is, but it's difficult to tell. Yeah, so an alpha decay, that alpha particle exists prior to the decay and tunnels out of the nucleus probabilistically, right, with whatever momentum, which depends upon its internal energy state. Okay. Here, if you go back to that previous board, you'll see that those particles, those electrons and positrons, didn't exist before the decay. They're the result of the neutrons and protons changing into each other. To conserve charge, they emit an electron, a proton. So the electrons, positrons, and neutrinos that are created in the nucleus but can escape since they don't feel the strong nuclear force. Okay? So these guys can just fly right out of the nucleus because there's nothing keeping them there, essentially. So maybe it's interesting to talk a little bit about how one detects neutrinos. This is a big area of science, particle physics, because as I mentioned, there's still some controversy about neutrinos and their properties. It's tied into quantum field theory and unified theories and stuff like that. Excuse me. So these neutrino detectors are giant tanks underground of the chemical tetrachloroethylene. So tetrachloroethylene is a fascinating chemical. It was actually first synthesized or made, or discovered, I guess, by Michael Faraday, so the same Faraday who did all the E&M stuff, and its most common use is as a cleaning fluid, right? If you've ever taken something to go be dry cleaned, like I take my blazers to be dry cleaned at the end of the semester, because I do sweat in them, they get gross. So if you've ever taken something to dry cleaner, you may think, well, how could you possibly clean something and keep it dry? They just vacuum it a lot. No, they soak it or wash it in non-aqueous chemicals, right? So that they don't harm the material the same way that water would harm the material. Water obviously is a very reactive chemical. It has a lot of things it does to materials, some of which are bad, right? If you're trying to keep your leather jacket in the same shape. So tetrachloroethylene is a way to clean things without water, but also it's really good at capturing neutrinos. So they have these giant neutrino detectors deep underground, usually in a mine or something like that. One of the famous ones is the Sudbury Neutrino Observatory, the SNO collaboration. And that's an old salt mine, I believe, in Canada. And miles beneath the ground, there's this giant tank of tetrachloroethylene. You can go and you can look at pictures. You can see pictures of people like floating in a little raft, and around them is they're in a raft of floating in tetrachloroethylene, and around them is all these detector equipment. So these giant chambers, which they eventually fill all up with tetrachloroethylene, and lining the chamber, this giant chamber in which the tetrachloroethylene is kept, are photodetectors. So neutrinos interact via the weak nuclear force with something in the tetrachloroethylene, I forget what, and produce a photon. Okay? And the photon flies out, and the detectors, the photomultipliers on the surface of the tank detect that photon, and then that's evidence that you did have a neutrino flying through there and hitting one of the tetrachloroethylene molecules. Why is it so deep underground? Well, you want to filter out all of the other particle interactions, right? So if you have a mile of stone above you, that's a pretty good way to filter out whatever other kind of radiation might be interacting with the material. It's an interesting side story that when they were first building one of these detectors, I forget which one, they ordered all this tetrachloroethylene to fill the tank, and the company that makes it, which of course had never made it for anything other than cleaning fluid probably, sent them untold thousands of hangers to go along with, as they thought, a nice little gift. So, oh, this is if you're a dry cleaning business, so you bought all this tetrachloroethylene. You clearly need a lot of coat hangers also, so I'm not sure what they did with them. Might be interesting to find out. An EC example would be chromium being turned into vanadium, I forget how to say it, and a electron neutrino. Right? So here in this process, only the neutrino escapes. Right? So not a very visible process, because the thing that gets out of the nucleus is the thing that's most difficult to see. Okay. So now that we know about all these different types of decay that can happen to the nucleus and radiate various types of particles, it's worthwhile to talk a little bit about decay chains. Right? So I'm going to draw a bit, well, maybe nearly all of it. I'm going to draw a picture from the book, but maybe looking in the book is a bit more clear. So this is the line of stability. This is N, this is Z. And we might start off with, say, thorium-232. So not on the line of stability, but it can alpha decay, losing 2 neutrons to protons. And so it's not parallel with the line of stability, remember, because the line of stability is not, you can't see, the line of stability is not at a 45-degree angle in this space, right? It's tilted towards the neutrons because they don't carry charge, so it's easier to stick in more particles. So this decays by an alpha process to radium-228. That decays by a beta minus to thorium-228. And then there's a bunch of alpha decays. I won't write all of them things, but alpha, oh, 4 alphas, alpha. All right. I won't write in all, so a bunch of alpha decays, and that becomes a radium isotope, a radon isotope, polonium isotope, and then a lead isotope, Pb. And then we have a beta minus, not quite to the line of stability, and that's bismuth. And then you can either become CO, polonium again, or a titanium isotope. And then either of these two processes finally bring you, after a beta minus or an alpha decay, down to 208 lead. Okay, so I'll step back so maybe you can see now. If I'm out of the picture, does it make it better? Okay, so these particle decays are essentially always happening in matter, right? Because most elements do not lie on this line of stability, right? You have to sort of wait for atoms to trickle down, and this is oftentimes called the drip line, this particular process, to a stable state that does lie on this line of stability, right? So this drip line swings back and forth across the line of stability, but none of these elements are exactly on it, so they're not stable, and then eventually we get, cat's knocking stuff off the table, eventually we get down to here. Okay. So now let's turn our attention to the nuclear force itself. And if this was difficult to read, it is in the book. It's on page 514. Okay. So we don't know the exact form of the nuclear force. We do know some characteristics of the nuclear force. Strong nuclear force. One, it is very strong. Okay? And it must overcome the electrostatic force, right? For it to overcome the charge, the repelling charges in order to form the nucleus. Two, seems to be the same between any two nucleons. Okay? Independent of charge. Three, it drops off very rapidly. Okay? On the scale of a few femtometers. So each nucleon only really feels the strong nuclear force of its closest neighbors. Okay? Because it's not like an inverse square law, right, where it more gradually drops off. It's really quite quickly that that potential well goes back up. So this explains, for example, the liquid drop model and some other simplifications with the nucleus, right? That you might think, well, if I add more particles to the nucleus, it should get denser as it gets compressed and crushed. But it's not the case because they don't feel the force from more distant particles. And there's another fact about the nuclear force that adds to this effect that keeps it from that keeps it at a constant density, which is that the nuclear force actually becomes repulsive at short distances. So, again, this is a contributing factor to the finite size of the nucleus, and that it has sort of this constant density because they don't want to be close to each other. They want to kind of be spaced out according to a specific structure. So, and 5, the force is spin dependent. So, at about 0.7 times 10 to the negative 15 meters, force is repulsive. At about 1 times 10 to the negative 15, it is strongly attractive. Should have planned this out better. And at about 2.5 times 10 to the negative 15 meters, it dies off quickly.